now that we've seen the algebraic approach, of course with a little bit of graphical approach snuck in there, let's actually look at the graphical approach for computing CT convolutions a little bit more closely. So the learning objectives for this section, of course, are to describe the LTI systems in terms of the convolution with the impulse response, manually compute some convolutions in the time domain, and use LTI properties to simplify your calculations, and standard formulas as well. So here again, we're looking for templates that we can reuse. Okay, so the graphical approach to convolution problems interprets the convolution integral as flipping or reversing x of tau and sliding it along by delays of tau t, or vice versa. You can flip h and slide it along x. So either way, you're going to get the same integral because convolution is commutative, and so it really just depends on which one graphically you find more appealing. And here's a screenshot from this demo that I mentioned in the previous video. So this demo, you can download it yourself from the Georgia Tech website, and we're going to use it to convolve these two signals. This is a box from 0 to 4, and this is a box from 0 to 2. So we want to convolve these two boxes and ask, okay, what happens when I convolve these boxes? What do I get? And remember, in discrete time, when we convolve two box-like signals, we get kind of a triangle or a trapezoid, actually, and here we're going to also get a trapezoid. So let's step through this. So at negative time, these two signals do not overlap at all. So the output is 0. So here again here we're flipping x of t and sliding it along h of t. But you could also, in the demo, you can click the other radio button and flip h of t, and then you could compute the integral the other way. Here we're doing it this way just to see what happens. Okay, we're going to see that the output signal is going to look like a trapezoid as we kind of maybe intuited from the discrete case. But let's see how it happens. So right, at negative time, these two boxes, the flipped version doesn't even overlap with the other signal. So the output is 0. Still happening, still 0. Keep sliding. Keep sliding. Keep sliding. Okay, now we can see that the two boxes, the flipped box and the H box, the box that represents H in blue, that one is, they're just barely overlapping. So the output is still 0 because they only overlap in one point. This is maybe unlike the discrete case where when you overlap at one point you get an output, but here, because it's continuous time, the integral of that multiplication is 0, so that's why you see nothing in this multiplication. Okay, now we start sliding across, and we're basically going to be integrating this overlap between the two boxes, and we're going to start increasing linearly as we slide across because we're essentially adding area under the curve at a linear rate because we're just getting a bigger and bigger box as we go along. So you can see we're sliding in, we're sliding in. Okay, now at this point, the two boxes overlap completely, and this is sort of the maximum area under the curve we're going to be able to get. And as we slide the red box further to the right, what's going to happen is that's going to be constant for a while, and then the red box will start to leave the blue box area, and we'll get this linear decrease. So you can see we're completely overlapping, still completely overlapping, and now there's only a partial overlap, and the box that you're integrating is decreasing linearly at a linear rate in area. So the area under the curve is decreasing linearly, decreasing, and then at this point the boxes stop overlapping and you get 0 again, and you're going to get 0 for all t bigger than 6. So in general, convolving these two boxes is going to give you a trapezoid, and hopefully you can see why from the example before, but if you can't see why, try to draw out another example for yourself, or use the demo, better yet, use the demo, try two different boxes in the demo, and then see if you can build some intuition about why you're going to get a trapezoid. We saw also that we have this 5-phase convolution that we had for the discrete time, But here in phase 1, we have x of t minus tau and h of tau don't overlap. And then you get a partial overlap, and you get a total overlap, and then you get another partial overlap, and then you get no overlap. So that's, again, these 5 phases of convolution when you slide 2 finite length signals across each other. And with boxes, you get this sort of increase linearly in the partial overlap and decrease linearly in the second partial overlap. And then the signal is, when there's total overlap, the output signal is a constant. So that's why you're going to get it. Increase linearly, constant, decrease linearly, you're going to get a trapezoid. So the same 5-phase method works for convolving 2 signals with finite lengths, like any 2 signals with finite lengths. And if the signals are complicated, of course, the calculations can start getting messy. So sometimes you have to maybe draw it out, and you can see better what's going on, and maybe you can get the algebra to simplify a little bit. And sometimes it's better to flip h and slide it across x. So you can compute, since the convolution is commutative, you can do this either way. You can compute x star h or h star x. And, somehow with the calculus, etc., it might be easier to visualize one versus the other. It might be easier to think about the calculation that you have to do with one versus the other. So let's try a couple more boxes. So why don't you try convolving these different boxes and see what you get. And remember, we can apply, so the key here is to apply the LTI system properties. So if I delay the input by something, then I delay the output by the same amount. So these boxes are not necessarily starting at 0, but we know how to convolve 2 boxes starting at 0. So if they aren't starting at 0, then you have to maybe account for the delay and then delay the output by the corresponding amount that you're delaying after applying the template. Similarly, I guess none of these have gains, so we don't have to worry about that. So really it's about applying the LTI system properties for delay.